All right, so it's a great pleasure to introduce a great scientist, legend of the Mexican mathematics and science, a friend of mine for many, many years, Alberto Verjovsky.
Thank you very much. I thank Professor Ludwig for this invitation. So, here's the title. Here we deal laminations, foliation, and so with the following. So, surface laminations, and the question with the laminations can be simultaneously uniformized in a continuous fashion. So, in the first place, a compact lamination is like a foliation, is a compact metrizable space L endowed with an atlas, foliated atlas, U alpha, T alpha, such that T alpha is a homomorphism from U alpha into a product D times T alpha. D is the unit disk in the complex plane, well, in R2, and T alpha is any topological space depending on alpha. Here I only will deal with T alpha is a Cantor set, or T alpha is a manifold. So foliation, in the case when T alpha is a Cantor set, this will be called a solenoidal surface because of the electric definition. So a solenoidal surface will be a topological space that looks like a disk times the Cantor set. So it wants to be, it looks like a surface if you take your glasses out, you think you just see a finite number of like a surface, no? But if you focus, then you see that it's actually a more complicated thing. And these things, laminations, appear constantly in normal mathematics, as I will show you. And so this is the definition of lamination. And when the ambient space is a manifold, and the T alpha are called the transversal. T alpha are open subsets of Rn, and the Phi alpha is smooth. Then this is the classical definition of foliation. Exactly, no? So here we changed a little bit by considering the transversal structure to get a arbitrary topological group, but in particular a Cantor set. More particular will be a Cantor group, which will be a profile completion of groups. No? So this is what I mean. And many questions. So using a metaphor by Dennis Sullivan, a solenoidal surface, namely one that looks locally like a disk times Cantor set, is like a diffuse version of a surface. It's obvious why it's called diffuse, no? Because, and the idea would be that you want the leaves to be smooth, and you want to do differential geometry longitudinally along the leaves. All the things you will learn from differential topology for our classical groups, we can do that that way. Continuity in the transversal direction. Those are the two conditions. And in the case of foliation, sometimes differentiable condition. So actually, in this two-dimensional case, we can identify R2 with C via the standard definition. Now, instead of thinking of the disk in R2, we take the unit disk in the complex plane. And if we impose on the atlas the condition that T alpha is holomorphic along the leaves, then this will be what we call a Riemann surface lamination. So it's a generalization of a surface. No? So many questions arise. Then there are many vector bonds that you can define. Everything that was defined here, the canonical bundle, you know, the quadratic differentials, the Beltrami differentials, tensor, everything you can do on a Riemann surface, you can do in a lamination like that. And in particular, you can speak of the complex tangent bundle and the canonical bundle, etc. You can define it in general the Picard group also, and in particular you can define a Riemannian metric, which is given by metric along the leaves that varies continually on the transversal direction, and locally is given the classical Gauss notation like that. So it has values in positive definite 2 by 2 matrices, symmetric matrices, and therefore you can speak of Riemannian metrics on that. And in particular, the here, I'm going too fast. So if we use complex notation as usual, like alphas or bears, for the Riemannian metric, is written this way. And as we know, to be positive definitely symmetric, we require that gamma be a positive real function and mu function less than 1. And this would be a Bertrami coefficient. And so we do exactly like a Bears, alpha pairs. We can do this completely the theory, no? As for quasi-conformal maps, measurable Riemann mapping theory, everything, just being careful to do, just being careful, no? Because this is not a surface. Have to take the transverse direction, take into account continuity or measurability sometimes. So the mu is called the Bertrami coefficient. It can be defined as a -1 form, so a section of the inverse of the canonical bundle times the conjugate of the canonical bundle. And the only regularity we ask in order to get good description of quasi-conformal maps are some regularity. But if you have two metrics on a compact lamination, then you have this inequality. So what to behave like a compact Riemann surface? In particular, you have a Riemannian metric. These have bounded geometry. What does that mean? That means that the curvature is bounded by compactness, and together also all its derivatives. So the fact that could be very complicated at least, but given any two metrics, you have this equality, and in particular, any two metrics impose on each of the leaves quasi-isometric, really quasi-isometric for any choice of metrics. In particular, it will make sense for a foliation. Well, let me continue. It will make sense for a leaf to be hyperbolic, parabolic, or elliptic, and that's given if I I'm in the compact case. Very hyperbolic means that the area of the leaf grows exponentially with radius. And for instance, you take a red foliation, and you have a torus and the classical red foliation, then the only way to give every Riemannian metric imposes that every leaf is of parabolic type, because the non-compact leaves are R2, but grow polynomially because approach the quadratically because they approach the torus, and therefore the leaf has to be R2, not the Poincaré disk, R2. And so you see that in particular with this condition, a leaf says, I'm hyperbolic, I'm elliptic, I'm independently of the metric you use. In particular, you can speak with the ambiguity of a hyperbolic foliation. Is given any metric, every leaf knows is hyperbolic. So the uniformization theorem tells you that any leaf is the universal covers either R2, the Poincaré disk, or S2. Let's take out S2 because of the famous Reb stability theorem. These are very not good. So I will consider only the case of laminations and foliations. So all these are hyperbolic. Make completely sense. And now the natural question comes to mind. Can I prove a foliated version, laminated foliated version of the famous Cube Poincaré-Klein uniformization theorem? In other words, I know that each leaf individually I can uniformize by the hyperbolic plane because I declare hyperbolicity. But the uniformization varies continuously in transverse direction. And the answer to that question is yes. I gave a proof for holomorphic foliations a long time ago. Alberto can then give another proof for general laminations. And the question now comes, can we use the modern techniques like Richard Hamilton proved the uniformization theorem using the heat equation? So is there a version of the foliated heat equation? And the answer is yes. Okay, so this is the theorem. So this here is what I told you. Makes sense to speak of hyperbolic lamination. Each leaf knows its conformal type. And this is the theorem that If L is a compact lamination by hyperbolic surfaces endowed with a laminated Riemannian metric, then there exists a laminated Riemannian metric G prime, which is conformally equivalent to the original one, and such that renders every leaf of constant curvature minus one. So now we can speak of geodesics, foliated geodesics, geodesic lamination, do the whole thing. We do that at a torso, for instance, in this sense. And well, as I propose, there makes completely sense to speak of the laminated Ricci flow in 2 dimensions, and I won't bother you with techniques. The proof is non-trivial, but obviously we know that it's true for surfaces, so we mimic, but you have to use some tricks of foliation, like existing of block tubes and some bounds. So finally, you can. This is a paper with Richard Muniz saying that, except to start running the Ricci flow and to be able to prove conversion, you have to start with a metric with negative curvature in every leaf. Unfortunately, there's a theorem of TNGs using the Hambana theorem that you can always, in the conformal class, change the metric so that every leaf is of negative curvature, not constant, but negative. And then you run the Ricci flow with that, and beautifully evolves. You don't have the Perelman problem of exploding, survives for all time, and converges to uniformization in a beautiful way. In fact, it's so powerful, this Ricci method, that the uniformization, the solution depends continuously on the initial conditions. So there's a canonical way to go for an arbitrary metric to a metric of constant negative curvature using the Ricci flow. Well, you use techniques, I won't bother you, but you have to do computations. You have the foliated Laplacian, and more or less the idea of the TNGs is because suppose you have a lamination that is the prototype of lamination is a principal bundle of a compact surface with a Cantor group. For instance, the profinal completion of the integers, or any periodic, and that would be a principal bundle, and everything is controlled by the monodromy, and will look like a flat bundle, except it has holes, no? It's the Cantor set, and therefore, if it's a Cantor group, it's a principal bundle. It has a hard measure along the Cantor fibers, and it has the Beck measure, Riemannian measure, along the leaves. And therefore, you have a measure that disintegrates as the Beck measure along the leaves, and vertically it's hard measure. And therefore, you can take the integral with this particular measure, we call the volume form of the lamination. With this one in particular, you can take the integral of the curvature, and voila, you have a Gas-Bonnet, a version of Gas-Bonnet. And that's what uses the TNGs to show that you can always perturb the metric in the conformal class, so to render every leaf with negative curvature. And then now you start the Ricci flow at that moment, and you have your uniformization theorem. So the paradigm that the idea, the metaphor of Dennis Sullivan that laminations, solenoidal manifolds look like surfaces is true in this particular case. Here are some. The important thing is that the Ricci flow, as we know, preserves the conformal type. It evolves preserving the conformal type. So we start with a arbitrary Riemannian metric, and at the end we have a metric of constant renders every leaf of curvature minus one, but it's in the same conformal class with the one you started. So it's very powerful. And this is the theorem. You start with any arbitrarily laminated metric, but I want a hyperbolic, and then you take a leaf-wise solution. There are some technical things, and you have an infinity evolves, and you have the solution to the uniformization theorem. This is the theorem I tell you, a compact lamination by surfaces of hyperbolic type. Then in each conformal class of the metric, there is one that renders every leaf. So this gives a different proof of the theorem, the old theorem I told you of lamination. A corollary, the hyperbolic metric G infinity depends continually on the initial condition. Therefore, if you take a set of all metrics, laminated metrics, with a topology of C infinity, meaning C infinity along the least continues in transverse direction, this is a Fréchet manifold, and you have a canonical retraction from one to the other via the Ricci probe. So essentially, the set of all metrics retracts strongly to the set of hyperbolic metrics. But you can also, in parallel, you can speak either metrics of hyperbolic metrics or complex structures. They intertwine one with the other by classical. So we can even speak of the laminated Teichm space of a hyperbolic compact lamination. Is defined as a set of equivalence classes of hyperbolic metrics, modulo that two are equivalent if one is obtained by the pullback of a laminated diffeomorphism, but which preserves the leaves. Because this principal bundle I was telling you, they are diffeomorphisms that don't shuffle the leaves, but it's a principal bundle. So the Cantor group acts transversally and shuffle the leaves. So I'm just considering the case of so this is a perfect definition of Teichm, and it's fantastic. The idea this comes from Dennis Sullivan. I learned that. In some particular case I will give you will be an infinite dimension Teichm space, but which is separable. We know classical universal Teichm space is not separable. It's like L infinity. But this one, the ones I will explain later, coming from some special solenoids, will be the first example by Dennis Sullivan of an infinite dimensional Teichm space with which is separable. Well, the ones I'm interested in is these beautiful solenoids which are called Nahor solenoid. Prove the following. Let S be a compact solenoidal manifold, namely one that is disk times a Cantor set, which is obtained as the inverse limit of infinite. So the canonical way is to take a compact manifold with residually finite fundamental group. In particular, for instance, I don't look, my eyes are not very good. So this is the surface, and I take the tower of all final covers of that surface. And take the inverse limits of that. Then this inverse limit will be automatically the inverse of points are finite set. So will be a Cantor set. If I will be a Cantor group because I'm taking regular coverage. So there's a deck transformation. So it's a profinite group, the fiber. And the beautiful theorem of Macquarie is if a solenoid is topologically homogeneous, then you can go from one point to another by homomorphic. If and only is an accord solenoid. Where Macquarie is solenoids obtained in this precise way. Inverse limits of finite coverage of a manifold with residually finite fundamental group. So this way you obtain an infinite number of beautiful examples. And in particular, you can start with a surface of Riemann surface of genus 2. We know every surface covers that. So you can start, there's this beautiful theorem that given this inverse limit, you can start the sequence from, you can crop the dead branch at the beginning and start at any level. So if you start with the surface of genus 2, you can also start at the surface of genus 3, genus 4, and so it will be extremely rich. So this is the particular types of, no, this is last page. I don't know what I'm doing. Oh, I think I did something that I don't understand. I think I need to watch. Where am I? Okay, here. Not here.
That's McCord.
Here, McCord. Here I was here, no?
Yeah,
So the definition McCord.
a little bit.
Eh?
Yeah, we should press one more time. Yeah.
Okay. So this definition are my universal beautiful examples, no? McCord Solenoidal. And it's beautiful theory of McCord, topological homogeneous is equal to paint the inverse limits. A beautiful theorem. This is theorem by Clark and Horder. A compact connected topological homogeneous solenoidal manifold can be obtained at the inverse limit of regular coverings if and only if it's homogeneous. So, give you this example. And this is what I was telling you is the creation of Dennis Sullivan to prove some very important theorems in dynamical systems relating to Julia said, the Feigenbach conjecture, and he started the study of triangular space of hyperbolic Riemann surface laminations L. Because of the correspondence between conformal classes of metrics, complex structure and hyperbolic structure of manifolds, one can define the triangular space LA as the space of continuous conformal structure on the leaves, and we only demand transversely to be continuous as usually, and exactly using the Tramic coefficient, exactly as we do with a compact Riemann surface, we do exactly the same thing. The national topology is Haldor, and it's by holomorphic and non-empty soft panel. It's a panic space for holomorphic quadratic differential, exactly like Alfred's pairs. And that comes the relation to Spencer, is in how many ways can I vary the conformal structure of that, so what I do. Well, suppose that it is the McCord Solenoidal manifold, which is the algebraic universal covering sigma, namely the inverse limit of all coverings of sigma. He called that the universal hyperbolic. This already was some of the ideas of the growth in this fundamental group. Use exactly not set of entire coverings, but this is this is what I told you. In this, you can start this from any. So one thing you can do is take a complex structure on the base and lift it to the leaves. In that case, you get 3G minus 3 parameters. But you can also, not every metric is like that. In fact, it's infinite dimensional. And this is for a dense set of laminated complex structure, the restriction, when you restrict to each, a cover is quasi-conformal map. So
you really like do this explanation.
Yeah, exactly. No, this is the except now you have to do that. The Duadi was that, but in this case you do that. Cantor said. No, look clear what you do, no. But okay, so you have that information. Well, this is the explicit construction. You take the order the normal subgroups by inclusion and take the inverse limit of the final coverings, and that's precisely and the final will be the profiler completion of fundamental group, Cantor group. But this and there's another possible definition. You take the upper half plane multiplied by the profiler completion and act like the suspension, act horizontally. So this foliation in particular here by a representation of the fundamental group of the surface into the group of homeomorphics of the Cantor set. They are like flat bodies. And therefore you can describe it that way, exactly like that. The lamination looks like H times G. G is a profiler group divided by G0. G0 is the fundamental group, enters as a dense subgroup. It's profiler completion. And then you have that. And you have canonical projection into the surface of genus G for any G. You can crop the lower branches. And well, it's a beautiful object. And then it's proved that time space of that is separable. In fact, the Stramer differentials that are the metrics that are locally constant is dense in the space of. As I told you, this is the first example of time-unit space. The reason it's separable, the deep reason, is the transverse continuity makes the lamination to behave like a makes it separable. In opposition to the standard time-unit space that is not separable space. So we have that. And she proved that the beautiful Ehrenpreis conjecture, which beautiful. If you can put it in the complex as a complex problem or as a hyperbolic geometry, you take two hyperbolic surfaces of different genus, one genus 2, one genus 4, with hyperbolic measures completely different. Theorem, there's a finite cover of both of them. Well, there's one cover of this one and another cover of this one of the same genus, so that these two are quasi-symmetric, epsilon quasi-symmetric for any epsilon. Namely, the geodesic of this one differ from the geodesic the marked geodesic spectrum of this one differ from that one. For instance, it's surprising, but if you ask the question for branch covering over P1, then you see that it's obvious in this case. So suppose you have a rational function R1. You have two rational functions. The pullback, canonically, the obvious thing, the pullback is a branch covering of both of them. So it's completely obvious in this case. So this is more subtle. You know, it's something that when I understood, say, it wasn't so, I sort of believed this. And this theorem was finally proven by Markovich and Jeremy Kahn. And this is the statement, you know. Had a big impact in topological hyperbolic manifold centers, a beautiful theorem. Dennis, and the consequence of this theorem is that if you take the universal time-unit space of these of Sullivan's, then the diffeomorphism group, the laminated diffeomorphism group, the diffeomorphism that don't shuffle the leaves, acts like the modulus space, but this time acts not like the modulus space. We know the one for the E is orbital, no? This one, the action is minimal. Is the consequence of this. So the modular group acts minimally. And that was very surprising. You know, it's a consequence of this theorem, and that follows. Well, that was Dennis. Now this is my contribution. Eves and Samson prove in the 60s a beautiful theorem. You have two compact Riemannian manifolds and a differential manifold from one to the other, such that the target manifold has negative curvature. Then F can be deformed homotopically to a unique harmonic path with respect to Riemannian metrics. Well, this theorem I prove it also for lamination. It's similar to proof, but has, and essentially the proof relies on, you see, you can define the energy function. You see, you integrate the square of the differential and use the Haar measure. For a surface, this is the energy function, and then the extremal points of this are by definition the harmonic laminated maps. And what happens if the solenoidal manifold of arrival is a hyperbolic lamination, then this energy function is actually a convex, strictly convex function, and the gradient of this function is a global attractor, and that's exactly the proof of Samson is. Many things you have to prove that regularity things. But that tells you that there's a unique map. There's a deformation from any map from one surface to another. Can be of different dimensions. So you let evolve it's the heat flow. The laminated heat flow works beautifully if the target manifold is a hyperbolic lamination. Well, here's just you have the tension field. You have sort of like the classical heat equation, Euler Lagrange, but I don't bother you with that. So this is my theorem. You have two solenoidal manifolds. The two are accord, namely obtain as inverse limits of covariance. You take any map which is differentiable along the leaves, and if the target manifold has metric of negative curvature, then the heat flow evolves and gives you a harmonic map. It's the same, exactly the same proof. And you may say it's not a photocopy of the proof because you have to work not too much, but I think the main idea here is to have guessed that it was true, no? It's maybe the biggest merit, no? Because there was no a priori reason. Okay. Well, here's exactly what I told you. The energy is strictly decreasing in convex function, and so it has a unique minimum, which is a global attractor. And the Danish homomorphic class of maps has a harmonic representation. And then there's this famous Earl-Eels theorem that describes Teichm space as a fiber bundle. It's a very famous paper in the Journal of Differential Geometry in the 60s. And it's the one I told you that apparently had great influence in Hamilton's ideas to use the Ricci probe. And so this is the theorem. You take the Sullivan lamination, you take the high heap is a set of all metrics of this lamination which are hyperbolic. They may render each leaf of constant curvature -1. It's a contrasted complex analytic manifold, a Frechet manifold infinite dimensional. This is the group of laminated diffeomorphisms that live invariant leaves, that don't shuffle the leaves. It acts continuously, effectively, and properly, and you have this fiber bundle description of orbits, and that gives you a fiber bundle description of this of Sullivan Tangent space. And in particular, you have this, that the group of diffeomorphisms is contractible. That was a very, very important theory of Eels and Earl, that the group of diffeomorphisms that are homotopic to the identity of a surface of G that's greater or equal than 2 is contractible. Why is that important? Because that allows you to classify surface bundles, the classification space, not surface bundles over anything. Well, as long as the surface of G is greater or equal than 2, then it gives you a very powerful technique. And this follows also in this case. The proof is novel after their work. And well, I won't bother with that. I better go to this one. So this is young work with my student, Elena Lizarra Colli. Actually, so it's the construction of new examples of foliations. So you do the following. So you start with a compact, with a complete, not necessarily compact. So I'm going to put a cusp here. Complete hyperbolic manifold of dimension 4. And associated to this surface, there's a twistor space to that. So these are the set of all. So this is tangent space at a point. It's like R4 with some metric. And the set of all complex structures at that point are set of, as you know, we don't know, it's set of all J's. So a J corresponds to the identity. And it's that in SO4, because there's a metric of that tangent space. and present the orientation. And so the center for complex structure is in particular is S2, no? Because it's for so you have a S2 bundle. Well, let's call it P1. You have a P1 bundle, which is called the famous twistor bundle. And now there's a beautiful theorem by, well, let me see. Beautiful theorem by, here's the reason why it's a sphere, you know. And there's a beautiful theorem by Attila Hitchinsinger. This one has a natural, almost complex structure, which is you take a point. So it's a P1 bundle. You take a point here. In the first place, the Levi-Civita connection gives you a horizontal foliation. So this is a P1 bundle over a four-dimensional manifold. We found the Riemann sphere, but it has horizontal distribution with fiber R4. No, but if you take in the horizontal, you have a natural J because it projects isomorphically to the base. And along the fiber is the sphere, so you have a J1, J2. They combine to give you an almost complex structure of twistor space for free, tautologically. And the great theorem of Attila Hitchinsinger is that in the case the manifold has a self-dual matrix, this almost complex structure is integral. And so we obtain a complex three-dimensional manifold. Real dimension 6, complex, and the manifold we got home really ready. And so this is a tautological bundle. This is the integrability condition I told you. If M4 in particular, if M4 is hyperbolic manifold, constant negative curvature -1, the twistor space is a 3. It's not scalar, but the horizontal distribution is holomorphic with respect to this. So it's a C2 bundle perpendicular to the fibers. And beautifully, because it's a holomorphic contact structure. So there's a one form with values in the normal form, in the normal on omega, or actually I call it theta, so that theta, wasted theta, is non-zero everywhere. So it's like a contact manifold, and therefore you have, makes sense to talk about the Youngsian curves and many beautiful things. And so this is the theorem. So now in that setting, now I have a complex manifold. My goal is to foliate this for manifold. Well, actually, is what I told you about the context structure. The Riemann-Civita connection gives you the horizontal, and but now there's a beautiful construction due to Ian Salmon. I think Professor Robert Bryan also did it. Is the following construction. So you have this for manifold, and you take a point and a two-dimensional plane, like plane R2, so the space of dimension 2 at that point. Then the metric tells you, and you're oriented to plane. Then this plane pi has a complex structure to rotate in the positive direction 90 degrees. The orthogonal plane also has a natural rotate in the positive direction 90 degrees. And therefore that gives you a point in the fiber. So this P1 sitting on this point, sorry here. This gives you a little point here. So the choice of a plane here, oriented plane, gives you a point in the fiber canonically, because it gives you a normal copy. It's true that several planes give you the same point. Which ones? Well, this transforms the plane, the tangent space of the four manifold into C2. And therefore the lines that are complex in this area, give you the same point. Okay, now what happens now is a beautiful theorem that is Earl-Sampson, is that if you take a totally geodesic immersion of the hyperbolic plane to here, it can cut itself, etc. Then there's a canonical way to lift it. Point by point, the immersion gives you a plane, an oriented plane, you can lift it. And therefore you lift it to a curve. So let me write the twist of space again like that. And so this totally geodesic space leads to a curve that is tangent to the horizontal distribution. In other words, a Legendrian curve. But the beautiful thing is holomorphic Legendrian curve. It's tangent to the horizontal, that is holomorphic. Now, let's do the following. The core manifold is covered by H4. Now here, I take absolutely all the totally geodesic planes, all of them. What are they? They are spheres, pieces of spheres that be orthogonally the boundary. These are the two-dimensional totally geodesic spaces. And I lift them all to M. And is that a foliation? No, it's spider web, it's a mess. So how do I construct a foliation of that? Then I remember the algebraic geometry monoidal transformation, and I do a global blob, namely, let me see. So here you have the twist of vibration. Here you have the horizontal distribution, and the horizontal distribution, I take the projectivization of that. So it's a P1 bundle over the twistor space. So now you have a P1 cross P1 bundle over the twistor space. P1 cross P1 is by holomorphic to the Grassmannian G42 of oriented two planes. So you have P1 cross P1, and now there's a canonical way to lift all this bunch of totally geodesic manifolds into holomorphic foliation, this four-dimensional non-Kähler complex manifold. And therefore, this gives you fantastic foliation. The important thing is that this foliation, because ergodic theorems of Rasner, Dani, etc., contains the geodesic flow, etc., almost every leaf is dense. So it's a very rich ergodic holomorphic foliation. Okay, and was obtained almost in some sense tautologically, but uses Attila Singer, uses Sal Reels to lift Legendrian foliations, and then uses Ratner's theories of ergodic theory of homogeneous dynamics together. But now, what happens if instead of taking spheres that meet the boundary at 90 degrees, I take the ones that meet it at 35 degrees? Well, these are not totally geodesic, but they have constant. It's easy to see that the group isometries of the disk acts beautifully in this space, and therefore they have constant Gaussian curvature, depending on the angle. If it's orthogonal, the Gaussian curvature is 0, and otherwise different. But then I take these spheres and move them, and there's a point in which they become tangent, and they become what is called Hort spheres. Now all this you can lift, and that's the Spencer theory, but geometric, not H1. All these foliations you are moving on. You started with holomorphic foliation, and moving this, you have a bunch of foliation. They won't be holomorphic, but doesn't matter. And then finally, when they are Hort spheres, all of these have zero curvature. They are isolated by planes. And therefore you go from hyperbolic foliation just by in your head moving spheres to ones with zero curvature. But nothing prevents me to put the sphere inside. So I take this sphere and push it inside. So this is a round sphere of radius, some radius, and this has positive curvature. And therefore, I can go from the holomorphic foliation by deformation to one that is flat, to another one that is foliated by spheres. And that gives you a construction very rich in dynamics, but was constructed completely geometrically. I think with that, I sorry for the little bit of mess.
Thank you very much.